I'm back in my office. We've got pictures to look at. And let's just see how this goes. We're in section 8.1. It's called sampling distributions. So what does that really mean? Well, for us, it means you collect a sample, you compute something, and you imagine reproducing that process over and over again. So you get a lot of different values from the sampling process and then computing something. And you take those computed things and you look at the distribution of those computed things. We're going to look at the average of values from normal data. So you have, say here, a normally distributed population. This is a sample. It's not very big, maybe a couple hundred. You'll still see a bunch of jaggies in there, but it's supposed to theoretically coming from a normal distribution. So in theory, if you kept doing this for a long time, you would get a bell curve like this. And so from what we're thinking is maybe it's mean 100, and maybe the standard deviation, mu is maybe 100, and sigma might be 20, yeah, to here, right? That might be 20. To here, maybe to here, like that. So something like that. And then we do the same type of thing, but this time we create 10 values from that distribution, add them together and divide by 10. So this is x bar, here is x, and that'd be 1 over n times the sum of the x's like that, with n equals 10. Okay. And then we take a look at that, and we look at that kind of carefully. I'm going to zoom in on that. Here we go. Since I can't really see it. Okay. So 6, 8, 10. Okay, so this looked like where 100 is, maybe here. I think I've got those numbers centered on the bars. Upstairs here, oh, I guess it's maybe centered on the bars, can't tell, okay. Okay, so mean might be 100, and then we're trying to guess the standard deviation. So it looks like it has some kind of a bell shape to it, still. And then you would guess maybe this distance here then might be the standard deviation. And this number down here, 246, maybe 106. So that might be 6 units. So we would guess, as we guessed for the top one, mu is about 100, but sigma might only be 6. So what it says there is that averages tend to have the same center, the same bell shape, but they're less spread out. And it's kind of unfortunate. This is a 6, even though it looks like sigma, that's a 6, and sigma equals 6. So it used to be 20 when it sampled individual values, but averaging 10 values reduced the standard deviation to 6. So it's not like tiny. You didn't divide it by 10 to make it 2. You did something else. So less spread out. So less spread out is good, because that means averaging gives you a better idea where the mean is, because the average tends to be close to the mean. And if there's less spread, then it tends to be closer to the mean than individual values. So the sampling distribution of the sample mean for normally distributed data has a normal distribution, same mean, smaller standard deviation. That's the upshot of what we seem to be seeing here. Now let's move on. So in fact, what I was saying can be mathematically shown. So you have to accept that the people that study probability and statistics, they have a way of determining that the mean of the sample mean is the population mean. And so in general, in all kinds of situations, and the standard deviation is the population standard deviation divided by the square root of n in all kinds of situations, not just here with normal distributions, but in general, that's just what happens. So we can figure out what we should have gotten for sigma for us, because it should have been 20 over the square root of 10. And we said that was about 6. I wonder how we did. Oh, look at that, 6.32. Amazing how things work out in advance. I hadn't checked this. So the mean then, if it was, it's 100 for both. And at sigma, this is the for x bar, and sigma for x was about 20. Okay, let's keep moving here, all right? Let's use that information. Now, what information was that? It says the mean of x bar is the population mean, and sigma for x bar was the population sigma over root n, like that. Okay. And we also know if x is normal distributed, so is x bar if we do simple random sampling. Okay. So we're assuming simple random. We need simple random sampling for a couple of purposes, mostly for this. The sigma over root n happens with simple random sampling. If you do something else, you might have a different kind of sigma. Okay, let's see. So we want to find the probability x bar is bigger than 115. It's found by then by finding z. So z is going to look like this: x bar minus mu over sigma over root n. So here's the thing, x bar, here's its mean, it's the population mean, here's its standard deviation. So that's the old-fashioned z-score applied to x bar. Use its mean, use its standard deviation. Okay. And the value we're thinking about is 115. The mean is 120. That's not what we had in our graph. Even though we thought the standard deviation was 20, we thought the mean was 100. Shall we do 100? What the heck? Let's do 100. Yeah. So that's 100 minus, 115 minus 100. Sigma is 20. Divide that by the square root of 10. Okay. So I'm thinking that might be a big number, because that's maybe 6, and that's maybe 15. Well, let's see what it is. So I go parentheses, 115 minus 100. I know that's 15. Divided by, and then parentheses again, 20 divided by the square root of 10. Go over, close up the parentheses. Okay. So you got to be careful. We're dividing by, so parentheses keep us from having the calculator do something silly. So that's guaranteed to work. So I get 2.37. I thought it might be kind of a big number. 2.37, okay. Z is 2.37. And we're looking at being bigger than. So I'm going to look in the tables. So I've got them here. 2.37 is here. 99, so 2.3 is over here. And 7 is up on top. There we go, 2.37. 9911. 9911. And so that would be the probability of being below. And we want the probability of being bigger. So I have to subtract that from 1. Okay, so our answer 1 minus 0.9911, which is, I think it's 0.089. Let's check it out though. 1 minus 0.9911. 0.0089, check, okay, did that. So that's our introduction to sampling distributions, and I'm going to stop this recording and start a new one in just a second.